Okay, so our third speaker is Patrick Rauer from DESY. He's going to talk to us about XFEL oscillators. It should be coming up automatically.
Perfect. Okay, yeah. Thank you first for the invitation. I'm glad to talk to you about the X-ray free electron laser oscillator, which is, I think, the first of the technologies, which is really an emergent technology as it does not yet exist at any facility. So there's a lot of projects coming up in the next few years, but not yet. It had not yet been realized. So most of the results I'm showing you will also be based on simulation, unfortunately. So, well, first of all, I'm giving this talk on behalf of the entire XFELO European XFEL team. So we are a couple of people from the European XFEL, DESY, and University of Hamburg. Then also thank you, Argo and Claudio. Oh, that's actually the wrong talk. Well, anyways, yeah, no, that's my fault, I guess. Yeah, I can still give this more reason. This is still my presentation. It's for another one tomorrow.
You just load all the other.
Yeah, well, let's give it from here. I guess.
It's the old one still.
It could be the old one, probably is. Yeah, it's the old one. Sorry. I'm sorry.
Can we see it on here?
Yeah. There. Okay, thank you. No, that's much better. Yeah, this one's the right one.
Cool.
I'm sorry. Okay, so it's just a little difference, but it's so thank you, Argo and Claudio, for laying the groundwork. So I don't really have to explain the SASA process or seeding as such, still to just give you the first idea. I mean, for SASA, we are starting from a stochastic electron source, and therefore also from stochastic radiation distribution, which even though going through a rather narrow bandwidth amplification will be very spiky in the end, will still be very stochastic. And a way to get rid of this is to use an external seed, either seeding directly the electron beam at the fundamental harmonic or the high harmonic, as we just heard. And then this imprints also this very high coherence, this very defined longitudinal state on the outcoming radiation. However, there is no direct high quality seed in the X-ray regime, also not coping what we heard before with the high harmonic generations, especially not in the hard X-ray regime, where the X-ray free electron laser oscillator is aiming for. So the XFELO basically is very simple. It is an oscillator, so just like the first laser oscillators or also FEL laser oscillators, you have two mirrors and you just trap the radiation in between these two mirrors. Now, there's a little trick to it, which is also both a problem and a merit. We do not have any mirrors in the hard X-ray regime which can do back reflection. Usually you only go up to some milliradian angular acceptance range. Now, however, if you just use periodic crystals by laws of Bragg's law, you basically couple a reflection of wavelength lambda to the crystal lattice spacing, which is an X-ray regime usually, with the incident angle theta. Obviously, in physics, we do not have any exact laws. It's more like a roughly. However, if you do the calculation correctly, you still get stuck with just 220 millielectron volt spectral bandwidth of this reflection. And these crystals, I mean, Bragg's law is also used for all the monochromators in the hard X-ray regime at X-ray facilities. Now, and this now serves, you couple it back in, and now you have not only seed, but you still have a monochromatic seed at this 20 millielectron volt bandwidth. Now, looking at how it actually works, the first round trip, just like I said, I mean, usually you have a rather short undulator for these devices, or a few undulator cells. You have a lot of synchronous radiation with some SASA on top, which is very spiky and has very wide bandwidth. Now, this reflection will then be reflected, this radiation will then be reflected at these two mirrors, which are monochromatizing. So it's the first round trip where you basically transmit 99.99% of your radiation, just couple a bit back, reflect a bit back, which is basically just just a part of the spike of the SASA radiation, which also will be much weaker in intensity, obviously. Now, if you do everything correctly and you overlap with your electron bunch, it's the next round trip, you seed these electron bunches, and after enough round trips, depending on the length of your undulators and the quality of your electron beam, you do see a clear spectral spike. And the more round trips you get, the more coherent, the more monochromatic your radiation gets, until in the end, you are promised with three-dimensional coherent radiation with very high spectral energy density. Comparing to the stars, and these are now from real simulation at 7 keV, you see on the time domain, SARS still gets to higher peak powers, which is just due to the course if we have very narrow bandwidth. Therefore, by the transform limit, we have a rather wide, rather long duration of the XFELO pulse. However, looking at the spectral domain, you see that's basically just the red line is the XFELO. You have a single spike of the SARS spectrum, and zooming into that, even, I mean, the blue line, I don't know if you see it, it's just down there on the bottom. You have roughly 6 orders of magnitude higher peak spectral flux being promised. So, and this with full pulse coherent and nearly transform limited. So as we even heard before, I mean, this can be very interesting for even time resolved inelastic hard X-ray scattering in the resonant or non-resonant nodes, for example, for the HED community, also for nuclear resonance spectroscopy, nonlinear effects. Also for high peak power applications, thinking about using this radiation as a seed for next undulator, afterburner. And what's especially interesting, I think, is we're moving closer to the optical lasers. So a lot of development we saw in optical laser science, we can basically port to the hard X-ray regime and see where this takes us to, for example, X-ray frequency comms and other things. Obviously, beyond our source, it's new challenges arises. I mean, it's also a reason why this thing has not yet been built. I mean, the first most prominent one is the matching. You have to match the electron bunches with the photons. And first, in the longitudinal domain, so in the time domain, basically you have to match the electron bunch repetition rate with the photon pulse round trip time. Now, looking at a normal conducting LINAC, just exemplary, took a 10 hertz repetition rate, you would have 10 to the power of 7 optical path lengths. So maybe we can construct an orbital XFELO, but I don't think that's very realistic. Now, looking at the lower limit of the UK XFEL, I think it's a little bit wrong. I think it's about 100 kilohertz. You're still at a multiple kilometer optical path length. So this also is, well, it's not impossible maybe, but it's very challenging. Now, looking at the European XFEL with its burst mode, we can go up to 4.5 megahertz. More usually run operation modes as 2.25 megahertz rapid. And this means only 132 meters optical path length, which is still pretty long. And looking at the second challenge here is the transverse matching between electrons and the photon pulses. And seeing that both of them are the micrometer scale, this basically means for this 100 meter optical path length that you need a nanoradian angular resolution for all your optical components in the system. Basically, by some gain FEL effects, you can go up to 100 nanoradian, which is state of the art for mechanics. However, it is very challenging to stabilize that. Now, another challenge, obviously, is the quality of the X-ray optics. I mean, it's not classic optics, so more you can expect the more effects are happening. You have this direct impact of the misalignment on the nanoradian scale. You have wavefront distortion introduced by your crystal mirrors or other mirrors you have in the system or lenses. Also absorption. Then there's the question of outcoupling. I mean, this is just stored in the cavity, and just like with classical laser oscillators, you need to couple it out somehow. There are a myriad of ways to do that. I will not get into detail there, but each has its own challenges and merits, basically. Then there's the tunability. I mean, a major advantage of FELs is this high range of tunability. But now looking at the Bragg's law, you basically couple your wavelengths to your incident angle. So if you want to make this thing tunable, you may have to make your crystals tunable. And this adds a lot of mechanical complexity to the system. And then there's a matter of feed load, which I would call the most prominent physical limitation of the system. I mean, it can also already say that you need very highly thermally conductive materials. So I think everyone who's working on these XFELOs thinks about using diamond, which is very radiation hard and very highly thermally conductive. And we still need cryogenic cooling to at least less than 100 Kelvin to get the heat away from the spot of incidence. Now, like I said, it's not been realized yet, but there are a couple of projects going towards realization. We already saw a slide on this cold cavity hard X-ray experiment at LCLS, where it's without an FEL, just the round trip basically of the system. Still, LCLS wants to realize the first proof of concept 2-bunch mode. I think my current status is at the second half of 2023 as a copper LINAC, and then in 2028, plus they want to build a real multi-bunch XFELO for the LCLS 2 high energy facility. Now at European XFEL, together with DESY and University of Hamburg, we want to realize the true multi-bunch proof of concept experiment in 2024, which is what I'm also going to be talking about in a while. And then there's the Shine facility, which is being newly constructed right now. They actually want to build, just with the start of the facility, a true XFELO beam line. However, it's not been built, and the plans are still a little bit obscure. However, this is really, they put a lot of investment into that. Now, for the proof of principle experiment at European XFEL, which is the one I'm working at, so it's an R&D project, which is meant to just prove the principle. So it's going to be located in the end of the SASA-1 tunnel. It's going to use the last 4 usually not used undulators, and it's going to be based on this 2.25 megahertz repetition rate. So the goal of that is to prove that seeding and also maybe stable operation is possible with the CBX, with the cavity-based X-ray FEL. So we want to keep it as simple as possible, to not obscure our goals with very high mechanical demands. And this is why we build it in the backscattering geometry, which means it's not tunable. We won't have any wavelength tunability for that. We're going to use Grayson incidence mirrors to detune the crystal some milliradian from exact 90-degree incidence, which is due to multiple beam excitation. I will not go into detail with that. However, these Grayson incidence mirrors have the additional advantage that by applying some surface curvature, we can achieve focusing, which is something we need for the 66 meters mirror-to-mirror distance. And by, this is very interesting, by putting all 3 mirrors at 90 degrees to each other, we form a so-called retroreflector, which is also known from optical science. And this retroreflector has a very amazing property that no matter the direction of the incident ray, the outgoing ray will always be antiparallel. So if the anti-chamber is vibrating with respect to the undulator, the outcome as the outgoing photon beam should still be antiparallel to the incoming one. This is inside the milliradian margin of our angular acceptance, obviously. And this is how a chamber is looking like. So you already see this is a pretty massive thing. I mean, there are more massive sources, but still is something we need to align to nanoradian scale. So this is going to be very demanding. So we have the pulsicule on top, we have the KB mirrors, we have the crystals, and a lot of diagnostic ports on it. Also, in order to maximize commissioning time, we will not use special electron bunches for that, but it should just work with your regular source operation bunches. And then later on, we can think about optimizing towards the next fellow. And it's using a very simple transmission scheme. So the outcoupling basically just uses regular crystals, 100 micrometer thick diamond. We will see in a while how this works. So this is basically the radiation from a full-scale simulation at 7 keV, including 100 radian mirror tilt, endocrine jitter from the source, and surface areas of the different crystals and mirrors we have in the system. And what we see is on the left side, the energy evolution that we actually saturate after only roughly 20 round trips with the at 7 keV and for undulator cells, and at stored inside the cavity up to 12 millijoule and pulse energy. So this is quite impressive, actually. The transverse profile is a little bit distorted. This comes from the imperfection of our X-ray optics. So this is also taking account of. And in the right side, we see the spectral energy density, which is 6 orders of magnitude higher than SASE. So this is, and also much higher than most other seeding schemes. However, this is for experiments that traps radiation. It's not the transmitted one. So the transmission is basically 0, there where our spectral peak is. And what we transmit is just the side wings outside this, outside the green curve. And this is how this looks like. I mean, you see it's basically a double spike. It has some imprint on it. So it's by far not as perfect. But still, it is 3 orders of magnitude, 2 to 3 orders of magnitude higher spectral flux than SASE. And like I said, just a proof of principle kind of experiment. And for that, this is still pretty impressive, I guess. Looking at, no, sorry, this was a mistake of this version. That in the time domain, you see it's not really transform limited anymore, but due to this hole in the middle of the spectrum, you also get some oscillations in the time domain. Now, coming to the problem of heat load I already touched before. I mean, what I just showed you before was without heat load. It was not taken into account. Now, you would have, with the system, 10 millijoule of pulse energy incident on the crystal, 2 megahertz repetition rate, and micrometer at micrometer source size. You can expect it to disturb to some degrees optical stability and the crystal spectral reflectivity. And now looking at the simulation I showed you before, this would introduce 600 microjoule of energy, heat load, into the crystal, which would give rise to more than 1000 Kelvin in temperature, and even waiting for the next photon pulse to arrive, which is the point of interest for us, we would still be above 600 Kelvin. This is much too high. I mean, I don't really have to show any additional simulation about that. You can see that this would not be working. However, we do not start at 10 millijoule, but we slowly build up to it. So the question is, if maybe we can reach lower pulse energy at stable XFELO at lower pulse energies. The answer is just putting it the way it is, it would not work. What we would have is this, so on top we see a logarithmic scale of the energy, and you see that it's basically periodically building up and dropping again. This is amazingly periodic. So it's basically between 20 and 21 pulses all the time. This correlates with a rise in the downstream crystal temperature. However, at the moment of this drop of the pulse energy inside the cavity, you transmit a very high fraction of energy with this basically full spectrum, this very narrow spectrum, in which is above 1 millijoule. So this is still a very high spectral flux, but only at every 20th round trip. You could call it a passively out cavity dumping scheme, basically. Nonetheless, there are methods to stabilize it. First is just reducing the FEL gain, for example, using less undulator cells or stretching your algorithm pulse a bunch more, where you can even go to 500 femtoseconds, 600 femtoseconds. Fully coherent operation, all by increasing your cavity losses. So what you usually do in classical optical lasers, if you have a lot of gain in the system, you increase the outcoupling coefficient to just get very high pulse energy out of the system. And just here, just was planning to just thinking about transmissive grating with, yeah. and transmissive grating, where you can basically just couple out like 10% of the radiation. It stabilizes the cavity, and we have the full radiation inside the system to make use for users. This, however, is not yet planned for the experiment, but maybe thought about as a future upgrade scheme. So coming to the summary, so an XFELO promises outstanding radiation characteristics. So with orders of magnitude highest peak spectral flux in SASE, and I did not go into detail about self-seeding, which is a competing mode for seeding at hard X-ray. It has a much higher shot-to-shot stability because it's basically averaged. And however, it's mechanically very demanding, and it needs a superconducting linac. These are the most promising, the two great challenges. There is the development of proof of concept experiments at LCS and European XFEL with a true, even though rather simplistic, multi-branch XFEL demonstrated to be commissioned in 2024 to European XFEL. The experiment may deliver intense pulses with very high spectral flux, which however suffer from the thermal response of the crystals. However, I can have shown you that meditation is possible, and there is just a starting point. There's a lot of different methods to go from there. So first, to take a matter, the realization of an XFEL is possible in the very close future, and looking at the timeline of the UK XFEL, one could think about an XFELO beamline. So that's it. So I want to thank you, and I'm open to any questions.
Thanks, Patrick.